All right, ladies and gentlemen, welcome back to another video with Mr. Kenton with HL Chemistry. We're continuing our discussion as we're moving through topic 1 with stoichiometric relationships. And now we're making a pretty big shift, right? Because everything we've been looking at up until this point has really been focused on masses, particles, and moles. And obviously moles we know is a big deal, but we're also going to start to look at how can we use stoichiometric relationships to describe how gases behave and how gases react, right? And so from this particular set of content that we're going to be looking at, we're going to be focusing in on Avogadros Law, which enables us to use the mole ratio of reacting gases to be determined from volumes of a given gas, right? And so we're going to be making that connection of how we can use volumes to make conversions to communicate information about the mole, right? So without further ado, this should be pretty fun, should be a pretty short video in comparison to the last one that you guys had to watch. So have fun, right? So Avogadro's hypothesis states that equal volumes of different gases contain equal numbers of particles at the same temperature and pressure. So what he's communicating, if you've got same conditions of temperature and pressure, and the volumes are the same, so let's say you have 5 liters of oxygen and 5 liters of hydrogen, they're both at the same temperature, both at the same pressure, that those gases, those volumes, those 5 liters of gas, each contain an equal number of particles in their container. That was a pretty big idea, it was a pretty big conclusion to make, and he was able to experimentally determine that particular hypothesis. So what that means is that if you are given gas volumes and asked for gas volumes at the same conditions, you can find your answer using the mole ratios without doing any conversions, which is kind of nice, right? And so let's just take a look at what does that mean? How does that set up? How can we use that piece of information? So, like I said, we'll be looking at how do we calculate reacting volumes of gases using Avogadro's law, because his hypothesis, it proves true over a lot of given circumstances. And so convert it into law, and we can use that to help us understand how gases behave. So let's look at an example problem. I think that's the best way to kind of analyze this stuff, right? So let's say that you've got, now this is a very IB thing that they like to do. Instead of using milliliters, IB likes to throw in here, we got our 40 centimeters cubed of carbon monoxide. Remember, that's just a volume, right? So 40 centimeters cubed of carbon monoxide is reacted with 40 centimeters cubed of oxygen in the following reaction. 2 moles of CO plus 1 mole of O2 yields 2 moles of CO2. And they want to know what volume of carbon dioxide is being produced in this given process. Well, you guys are intelligent human beings. You also notice they gave us a second quantity. So we got that 40 centimeters cubed of oxygen. This is a limiting reactant problem, right? They have disguised this gas problem as a limiting reactant problem. Maybe they didn't disguise it. They didn't do it very well because we noticed there were 2 things that were given, but I digress, right? So this is actually a limiting reactant problem and volumes of gases problem, and this is pretty typical. You probably saw this on the AP exam. If you're planning on taking the IB exam, you would probably see a question like this. So just kind of know that moving forward that IB loves to disguise limiting reactant problems using volumes of gases, okay? So we got our 2 givens. Let's figure out what volume of carbon dioxide can be produced. Right, so we've got our dimensional analysis, we've got our stoichiometry, and we're setting up in terms of our given versus needed. So for our carbon monoxide, we need 20 centimeters cubed of oxygen. And with our oxygen, we need 80 centimeters cubed of carbon monoxide. Well, last time I checked, we're only given 40 centimeters cubed of carbon monoxide. So our carbon monoxide is our limiting reactant, right? So we cross-reference that information. And so because of how volumes work, we don't have to worry about using the conversion factors to where we need to go from centimeters cubed to moles, because we know that those equal the same amount of particles, right? And so you can use the mole ratio directly without converting centimeters cubed to moles first, which is kind of nice. It saves us a step or two of having to do a conversion factor. So we need 80 centimeters cubed of carbon monoxide and only have 40 centimeters cubed. So carbon monoxide is our limiting reactant. And so the amount of carbon dioxide that we can make is going to be 40 centimeters cubed of carbon dioxide, because we use the mole ratio 2 moles of carbon dioxide for every 2 moles of carbon monoxide that react. Oxygen is in excess by 20 centimeters cubed. Now, other thing we need to incorporate here is there is a conversion factor to be able to go from volumes to moles, and it's important for us to recognize those. So the molar volume of an ideal gas is a constant at specified temperature and pressure. Now, at standard temperature and pressure, STP, so remember those conditions, 273 Kelvin, 0 degrees Celsius, and 101.3 kilopascals, or 1 atmosphere, our conversion factor, or our constant, is going to be determined by using those conditions. Now, if you don't have a calculator, you can just simply use 100 for 101.3 kilopascals to kind of get your answer in the ballpark. And then room temperature and pressure, another set of conditions that you need to be aware of. RTP, not the Research Triangle Park, but RTP, 298 Kelvin and 101.3 kilopascals. So the molar volume of a gas at STP is 22.4 decimeters cubed per mole. Again, this is a very IB thing for them to do, to give you decimeters cubed per mole. It's the same thing as liters per mole, but IB likes to use the standard units for volume, or I guess the base unit. And remember, volume, since it's essentially length times width times height, the unit for length is the meter, and so that's why we've got decimeters cubed per mole here rather than liters per mole. So that's at STP, 22.4. And then at RTP, the molar volume of a gas is 24 decimeters cubed per mole. Now notice that there's a slight difference in our volume from standard temperature and pressure to room temperature and pressure. And we're going to kind of analyze and dive into that, but I want you to think about, how does that pertain to kinetic molecular theory? Okay, so that's all I've got for this video, guys. Thank you guys for tuning in. Hope this was helpful. Hopefully it was a good little review of information that you already know, and I look forward to seeing you guys again real soon. Take care.